Internet? You want to say hello to the internet? It's okay, nobody's paying attention. Nobody's watching. But just in case. We're going to start today with a couple of definitions that you've probably heard before, but that I want to make sure that we get right, because they may be a little bit different from what you've heard in the past. We're going to start from the very general, and then we're going to talk about how this actually influences everything from like how we make measurements in a lab every day, even these kind of big, lofty ideas of science. So you've seen these words before? Law and theory? These words are a little bit tricky. The reason they're tricky is that they have meanings in different areas. We use these words in our everyday lives for various things, but we also use them in science. And the scientific definition of these words is going to be a little bit different from how we might use them in our everyday life. So either an everyday decision or a scientific, or everyday context or scientific context. Somebody give me a definition for one of these. How do you, that doesn't have to be a formal definition, just how do you think of one or the other of those terms? What do you think of when you think of those things? Yeah.
Law, I think it's like proven, it's like a fact.
So a law is like a fact, something proven. Okay, what else? Thanks.
It's something that you go by in daily life.
Something you go by in daily life, like a rule. Can somebody give me an example of a scientific law?
Gravity.
Law of gravity. What else?
Conservation of matter.
Conservation of matter. Sure. Newton's laws, stuff like that. What about a non-scientific law?
Speed limit.
Speed limit? Yeah. Yeah, okay. All right, let's move on to theory then. Nobody want to talk about that. What is a scientific theory? And notice I haven't written anything down yet because we're going to get into what's right here. What do you think of when you think of a scientific theory?
Like a hypothesis.
Something about a hypothesis? Sure. Yeah.
An idea that's backed by scientific knowledge but is liable to change.
An idea that's backed by knowledge but liable to change. Okay. What's an example of a scientific theory? Do you know any of those?
Pangea.
Pangea. So the idea that the theory that all the continents were once one large continent a long time ago. Okay. What else?
String theory.
String theory. Yeah. I don't know a lot about that. That's physics. The idea that all particles can be formed by these vibrating strings, that, right? Something like that. Anybody know that better? We want to explain string theory. Sorry, not a physicist. What else? Relativity, theory of relativity, sure. Atomic theory, the theory that stuff is made up of atoms. So those are some examples. What are some, well, maybe this doesn't work as well. I was going to say what are some non-scientific theories, but we don't necessarily have good examples of those. So let's talk about the proper definitions for these scientifically and how they might differ from how you have heard them before. So scientific law refers to a set of observations. Another way we might think of this is what happens. So you do this, this happens. You do this, this happens. You do this, this happens. You do that enough times in enough situations, and you formulate this law that whenever we do this, then this thing seems to happen. That's what a scientific law is. So something like a law of gravity, we notice that everywhere in the universe, when masses encounter each other, they attract each other with a force that's proportional to their masses and the product of their masses and inversely proportional to the square of the distance between them. That happens all the time, so we formulate this law of gravity. Think, what else did we come up with? Law of conservation of matter. You do chemical reactions and you find that matter is neither created nor destroyed. So then a theory relates to this, but it's a little bit different. If somebody said to you, hey, I've been making these observations and I keep seeing the same thing happen, And I'm going to call it Joe's law because it keeps happening, right? And I've got all this evidence to back it up. What might you ask me?
Why?
Yeah, why does this happen? And as I've formulated this law, I don't know, I just keep seeing it happen. But ultimately, I then want to formulate a hypothesis or a theory about why that is happening. So a theory is the reasons for the observations why it happens. So if I take this theory as a hypothesis, then I can explain all this other stuff. If we take Pangea as a theory, then we can explain things like why certain fossils are spread across the whole world. Or if we take atomic theory, if we say that things are made up of atoms, then we can explain their behavior through the behavior of atoms interacting with each other. So it's the why, it's the what's behind the scenes here causing these effects that we're seeing. So a law requires evidence to back it up. And a theory also requires evidence to back it up. They can also both be refuted by contradictory evidence. If there's a preponderance of evidence against a theory or a law, then we have to say that that's not really a law anymore, or we have to put some qualifications on there. Good example of that, somebody said the law of the conservation of matter. Matter is neither created nor destroyed. Well, anybody know what the exception is to that? Yeah, nuclear reactions actually do destroy matter, or can destroy matter, can turn matter into energy. So once we started investigating those sorts of reactions, we realized, well, actually, there is some evidence against the law of conservation of matter, and really it should be a more specific law. So now, anybody know how we say the law of conservation of matter now? We still say matter is neither created nor destroyed, but only in certain situations. Anybody know what situations? We say in a chemical reaction. So in a chemical reaction, matter is neither created nor destroyed. But in a nuclear reaction, it can be. So we had to refine that law based on evidence against it. Same thing with Newton's laws. Right? Newton's laws explain motion, work really well. You can calculate a projectile and see where it lands somewhere else. Did you do that kind of stuff in physics maybe in high school? Where do Newton's laws break down? Anybody know? What do Newton's laws not work for?
Anywhere not that's on Earth.
Kind of, yeah, kind of. Maybe more specific than that. It doesn't work for things that are really, really big, or things that are moving really, really, really fast, or things that are really, really, really small. So when we talk about things like the motion of a missile that you shoot, Newton's laws work really, really well. When we talk about the motion of an electron moving around an atom, Newton's laws don't work at all. We need something called quantum mechanics for that. So that's kind of the breakdown of the law, the evidence against the law, and we have to then refine that law to fit that evidence. It's the same thing with a theory. A theory requires evidence, and various theories can be supported or unsupported or negated with evidence. So things like atomic theory, we can pretty much see atoms now with fancy new microscopes, or at least get really close to that. For a long time, we couldn't. So the atomic theory said, if stuff is made out of atoms, then it should do all this stuff. And then as it keeps fitting those predictions, then we have more evidence to support atomic theory. And do you know anybody who would argue with atomic theory or say it's like not really proven? Probably not, right? Most people are good with the idea that stuff is made out of atoms. And so that kind of is a good counterexample to this popular idea that a theory is somehow less proven than a law. Like a theory is like a baby law, and when it gets enough evidence, it becomes a law. That's the popular assumption. That's the popular definition. That's what most people think of when we say theory and law. But it's actually not true. It's actually not true. Neither one is more proven than the other. They both require evidence, and they both can be negated by evidence. And so that's an important distinction. If that's not something that you thought in the past, try to change things around a little bit so that you do see that. A weird thing is going to happen. If I asked everybody right now to define theory and law, we just talked about it, you'd all say what we just said, and it would be good. But in a few weeks, we're going to have a quiz or exam or something, and this question is going to come up. What's a theory? What's a law? And a bunch of people are going to get it wrong. A bunch of you are going to get it wrong. I mean, maybe not you, but historically, a bunch of people got it wrong. And it's because it's this well-documented effect that when something is so deeply ingrained in your brain, like a definition for something because you've thought that way for your whole life, even when you're presented with the true information, if that true information is against what you think deep in your brain, you're going to revert back to the old way because it's so deep in there. So it's a weird thing that happens. So make a little star on your notes in this, or make a little note somewhere, or set an alarm on your phone so every week it reminds you that this is the correct definition of law and theory, and eventually you'll be able to kind of break out of that. But it is a weird thing that happens. So why, I mean, other than just general knowledge, we actually have to talk about these because it influences something that we do in lab all the time, which is measurement. All right, so now we're going to talk a little bit about measurement. How many people here have measured something before? Who measured something, let's say, in the past day? Mind sharing? What did you measure? A piece of wood? Okay. What did you measure it with? A ruler? Okay. Anybody else? What else have you measured the past day? Did anybody measure anything in the past day? What about the past week? Did you measure anything in the past week? Yeah, what did you measure?
Olive oil for cooking.
Olive oil? Okay. How'd you measure it? Measuring cup? So when you, was it like a measuring cup that has the different lines on it for different amounts? Do you remember how much you had to measure? It's not really important, but if you do.
I think it was like, yeah.
All right, can we say half a cup? Does that seem reasonable?
No, that's what?
That's a lot of oil.
Yeah, no, it was way less than that. Like
Oh, okay.
4.
I didn't know it. Wait.
Wait, no, that's more. it was like that one.
Okay, we'll say a quarter cup.
Let's just say that.
Quarter cup is 4 tablespoons? No. Yeah, 4 tablespoons. So, all right, we'll say that. So anyway, when you measured it, you like pour it in and there's a line or something, right? How did you know that it was exactly at the right spot?
I looked at it.
You looked at it? How'd you look at it?
My eyes.
Okay, yeah. I mean, did you hold it up? Did you put it down? Like, how did you know that it was right at that line?
I held it up and I looked at the line to make sure it was at the line.
Okay. And how sure were you that it was exactly the right amount?
I'm not 100% sure. Maybe it might have been a little over.
Okay. Yeah, and I'm not trying to like insinuate that you like mismeasured your olive oil or something, but the reason I'm asking these questions is that these are questions that we would ask about measurements in the lab that we may not ask about our measurements outside of the lab. Like when you, after that, you didn't think like, oh, how do I make sure that this is exactly the correct measurement? You don't. You say like, okay, it's about there and it's fine because that's what the cooking requires. In a lab, we need to be a little bit more precise with our measurements. And actually, we need to know exactly how we write down those particular numbers. So can I ask you about your wood measurement now?
How long was it?
Do you remember? Okay.
It was probably like 10 and a quarter
10 and a quarter
inches.
inches? Okay. And you say you use a ruler for that? And did you said about 10 and a quarter, so I'm guessing you didn't like zero in exactly. But there's a judgment call there, right? If you look at a ruler, you've got your gradations or whatever, and then at some point you have to say, well, where is this? Because is it exactly on the line? Is it somewhat on the line? And sometimes, depending on what our measurement requires, sometimes we just guess. Sometimes our context dictates what we write down. This actually all comes into a really big idea in science, which is uncertainty or doubt. Why is uncertainty or doubt important in science? Anybody thought about this before? What does it mean to have doubt in science or to have uncertainty in science? Nobody? wants to give it a try?
You're not certain, you're not sure that it's correct.
You're not sure that it's correct. And so if you can actually quantify how not sure you are, that's pretty powerful because it communicates to other people how much room there is in it. How much room there is in it. The important thing about that is it makes science different from other ways of knowing things. So before the scientific method and all that, how did people know things? Before the idea of experimentation and science, how did people, like if you were living somewhere in, I don't know, the year 900, how would you find out stuff? How would you learn stuff? Stories, right? And so who would be in charge of the information, generally, in those types of situations? You know? It was usually like kings or religious leaders. So you learned through what we call authoritarian means, meaning somebody in charge decided what is true, that got filtered down, and then people learned based on what the people in charge said. So whether it was right or wrong, if the king says that the world is flat and, you know, whatever, then that's what it is, and that's true. And if you contradict that, probably not great things are going to happen to you, right? So when the scientific method comes around, it's actually a very, very dangerous idea that you could doubt this knowledge, that this knowledge that has been passed down from the highest authorities of kings and popes and whatever else, that you could doubt that and say, I don't think that. I don't think so. I'm going to go gather my own information, my own observations, my own evidence, and I'm going to come to my own conclusions. And so you can imagine what happened to a lot of these people, right? And of course it did. They were killed. They were thrown out of the society, whatever, for doubting this authoritarian rule. But now, although we have our own issues with authority and such, you know, I don't want to downplay that, but if somebody says that something is true in a scientific way, you can go repeat that experiment and verify if it is true or not. You can doubt their conclusion. You can go find your own information and either support or go against that conclusion. And that's a huge difference, right? That's revolutionary. The idea that anybody, you don't have to be, you know, if the most famous, well-regarded scientist in the world comes out with some big pronouncement on something, and this has happened many times. We're going to talk about one in particular later in the semester. A big famous scientist comes out with a conclusion about something, and you're not a big famous scientist. I don't know, maybe some of you are. Nobody said so in the introduction, so I'll assume you're not. We're not big famous scientists, but we could go repeat those experiments. We could do our own experiments, and we can go prove that that big famous scientist is actually wrong. And other people will believe us based on the strength of our data. And so that comes into things just even as basic as taking a graduated cylinder measurement, a graduated cylinder reading. If we allocate the appropriate amount of doubt, then we're being honest scientists, and we're saying that in the future somebody may contradict us, and we will understand that there was a certain amount of uncertainty in our conclusions. So when we write down a number from a graduated cylinder, we have to make sure to build in the appropriate amount of uncertainty. And so any number that you write down is going to have an uncertain digit in the rightmost number. And we'll usually just record one uncertain digit. So we're going to have a bunch of digits that we're absolutely sure about. And then we're going to have one that is estimated. And that's always how we're going to make our measurements in this class. So let's look at this graduated cylinder on the left. You see a liquid level there, right? And you see some lines in between 70 and 80. Anybody know from your previous chemistry, where do we take that measurement? Do we take it from the bottom? Do we take it from the edge? The bottom, right? The very bottom of that curve. So we have to make kind of a judgment call as to where that bottom is. But there are some things that we can be pretty sure about. For instance, I would say that that is between 70 and 80. Do you think anyone would disagree with me that that's between 70 and 80? No, it's clearly shown that here's a line for 70, here's a line for 80, and our liquid line is somewhere in the middle. There's not really much controversy there. So we might write down a 7 as our first certain digit. We know that that number is going to start with 7. what else do we know? I think we can be pretty certain that that bottom of that line falls between the third and the fourth tick. Would you agree? I don't think we can really make an argument that that number is not between the third and the fourth tick. So that means that our second number is also certain, 73. Now, we're no longer sure. Now we're in the kind of vague middle area because we're in between those little tick marks and we don't have anything to guide us where we are anymore. So our very last digit is going to be our uncertain digit where we estimate where the level is. So looking at that, what would you call that last digit? 73 point, what? 25? Well, we only get one digit. We only get one. So you're going to say 4? All right. Can we get a different one? Where is that? 3? Do we see anything different? So it looks like it's less than halfway between the two tick marks. So probably 3, 4, something like that. All right, so we'll say 73.4. And I put it in red to show that that's our uncertain digit. All right, now that's a correct measurement. And our uncertain digit is generally implied to be plus or minus 1 in the rightmost digit. So that means that when we write down a measurement of 73.4, we are communicating to whoever is reading that measurement that our reading is somewhere between 73.3 and 73.5 milliliters, a difference of 0.2 milliliters. And that's why that number is so, well, that's why it's so important to have exactly the right number of digits when you write down your measurement. Because you're not only communicating the reading, you're communicating the uncertainty in the reading. You're communicating what the possible range is. If, let's say, oops, line there. If you weren't thinking about exactly the number of digits to write down, you might say that and say, well, okay, it's 73.40, right? Okay. So what's wrong with that? This communicates a different range. If we write 73.40, that means that we're communicating that that measurement is between 73.39 and 73.41. That's a difference of 0.02. So that's a 10 times more precise measurement than 73.4. Even though it's just a 0 at the end, and we think about 0 as not meaning anything, by putting that extra significant digit, we have communicated a totally different measurement than what we actually took, a 10 times more precise measurement than what we actually took. And that's why that is important. So now, so we're going to say, that's not correct. So now let's try that same idea with this thermometer and this liquid measurement right here. So I want you to look at those two scales, the temperature and then the liquid level, and write down what you think would be an appropriate measurement to report based on the right number of digits. So you want all of the certain digits plus one uncertain digit. See if you can come up with a measurement for each of those. And based on where you're sitting, you know, there might be some more variation than if you were really staring at this thing, but well, that's fine. So everybody got some measurements? Write some down? All right. What do you think for that thermometer? What's that? How should that temperature be reported? We want to give it a try? 88.2. 88.2? Make it something different? Anything different? 88.7? Okay. Anything else? No? Nobody else got any? Or you got the same things? Can we say anything? Okay. So we know for sure it's 80. It's between 80 and 90. We know for sure it's between 88 and 89. And then where we see that line ending is going to be how we estimate that last digit. So something like 88.2, 88.3. As I'm staring really close at it, it even looks like it could be 88.4. But either way, that's going to be an estimated digit depending on how you interpret where the end of that line is. All right, so what about the blue liquid over here? What did you call that one?
645.
645. Okay, anybody get something different? Yeah. 643. Others? Same kind of stuff. Okay. Yeah, I think that's reasonable. So it's the 600 for sure. It's above the 4th level for sure, not up to the 5th. So it's 64. And then that last digit is going to be estimated. So 643, 645, depending on how you see where that line ends. The point of all this, and the thing that is going to be important for this entire class, is that the number of digits is not arbitrary. Meaning that you don't get to just, in science, you don't get to just look at the thing and say, it's about 640. You have to make that distinction for each tool you use. How many digits am I going to write down? And it has to be correct. It has to be, it's controlled by the device that you're using. Whatever tool you're using is going to have a certain amount of precision built in, and you are responsible for writing down the measurement using the appropriate amount of precision, not more and not less. So you can't throw extra zeros onto the end just because you feel really good about that measurement. And you can't round it just because you want some nicer numbers. All right, so we're going to be very sure when we work in lab in this class to always take our measurements precisely. What happens if you're working with something like a balance? Our balances in the lab are digital. So you might get something, you weigh your stuff out and it says 1.234. How do we deal with uncertainty in that measurement?
The last digits around it.
Yeah, the last digits actually already has that uncertainty built in. So if you look at the balance, like in the instructions or kind of on the side, it'll say plus or minus 0.001 or sometimes 0.002. So you write down all the digits that the balance or any other digital instrument gives you, and you assume that the last one is uncertain, has some uncertainty. So you don't ever round the stuff that you get from a digital instrument like that. You write down all the digits all the time. Sound good? Questions? All right, let's stop there. We'll pick up on Thursday or Wednesday tomorrow, talking about precision and accuracy and significant figure calculations, that kind of stuff. So should be fun. Please turn in your, please give back your pretest and your information form in 2 separate piles on your way out. And let me know. I'll be around in my office until I have another class at 12:30. So if you need to talk or whatever, I'll be there. Otherwise, I'll see you in the morning. Afternoon, tomorrow.